The 555 timer IC is an integral part of electronics projects. Be it a simple project involving a single 8-bit microcontroller and some peripherals or a complex one involving system on chips, SoCs, a 555 timer is involved. These provide time delays, as an oscillator and as a flip-flop element among other applications. The 555 timer is a very common IC designed to generate a wide range of electrical voltage waveforms. For example, by connecting an external RC circuit to the timer, it is easy to generate pulse, step, and square waveforms. In this tutorial, we are going to introduce this IC and check its different components and how it works. The basic 555 timer gets its name from the fact that there are 3 internally connected 5K resistors which it uses to generate the 2 comparators' reference voltages. The 555 timer IC is a very cheap, popular, and useful precision timing device which can act as either a simple timer to generate single pulses or long time delays, or as a relaxation oscillator producing a string of stabilized waveforms of varying duty cycles from 50 to 100%. The 555 timer chip is extremely robust and stable 8-pin device that can be operated either as a very accurate monostable, bistable, or astable multivibrator to produce a variety of applications such as one-shot or delay timers, pulse generation, LED and lamp flashers, alarms, and tone generation, logic clocks, frequency division, power supplies, and converters, etc. In fact, any circuit that requires some form of time control, as the list is endless. The 555 timer chip consists of 25 transistors, 2 diodes, and 16 resistors in the form of 2 comparators, a flip-flop, and a high current output stage. Any 556 oscillator timer is another chip where 2 555 timers are combined together. Low-power CMOS versions of 555 timers, such as the 7555 and LMC 555, that use MOSFET transistors are also now available. In the figure, you can see a simple diagram of the internal circuit of the 555 timer. Given a brief explanation of each of its connecting pins to help provide a clearer understanding of how 555 works. Pin 1. Ground. The ground pin connects the 555 timer to the negative 0V, a supply rail. Pin 2. Trigger. The negative input to comparator number 1. A negative pulse on this pin sets the internal flip-flop when the voltage drops below 13 VCC, causing the output to switch from a low to a higher state. Pin 3. Output. The output pin can drive any TTL circuit and is capable of sourcing or sinking up to 200 mA of current at an output voltage equal to approximately VCC. 1.5 V. So small speakers, LEDs, or motors can be connected directly to the output. Pin 4. Reset. This pin is used to reset the internal flip-flop controlling the state of the output. Pin 3. This is an active low input and is generally connected to a logic 1 level when not used to prevent any unwanted resetting of the output. Pin 5. Control voltage. This pin controls the timing of the 555 by overriding the 2-3 VCC level of the voltage divider network. By applying a voltage to this pin, the width of the output signal can be varied independently of the RC timing network. When not used, it is connected to ground via a 10 NF capacitor to eliminate any noise. Pin 6. Threshold. The positive input to comparator number 2. This pin is used to reset the flip-flop when the voltage applied to it exceeds 2-3 VCC, causing the output to switch from high to low state. This pin connects directly to the RC timing circuit. Pin 7. Discharge. The discharge pin is connected directly to the collector of an internal NPN transistor, which is used to discharge the timing capacitor to ground when the output at pin 3 switches low. Pin 8. Supply plus VCC. This is the power supply pin, and for general purpose TTL 555 timers is between 4.5 V and 15 V. As we mentioned earlier, the name of the 555 timer comes from the fact that there are 3 5K resistors that are internally connected to each other in this timer. These resistors make a voltage dividing network between the supply voltage, pin number 8, and the ground voltage, pin number 1. The voltage across this network of series resistors keeps the negative inverting input of comparator number 2 at 2.3 VCC and the positive non-inverting input of comparator number 1 at 1.3 VCC. The two comparators produce an output voltage dependent upon the voltage difference at their inputs, which is determined by the charging and discharging action of the externally connected RC network. The outputs from both comparators are connected to the two inputs of the flip-flop, which in turn produces either a high or low level output at Q based on the states of its inputs. The output from the flip-flop is used to control a high current output switching stage to drive the connected load, producing either a high or low voltage level at the output pin. The most common use of the 555 timer oscillator is as a simple astable oscillator by connecting two resistors and a capacitor across its terminals to generate a fixed pulse train with a time period determined by the time constant of the RC network. But the 555 timer oscillator chip can also be connected in a variety of different ways to produce monostable or bistable multivibrators, as well as the more common astable multivibrator. Monostable multivibrator with 555 timer. The operation and output of the 555 timer monostable is exactly the same as that for the transistorized one we looked at previously in the monostable multivibrators tutorial. The difference this time is that the two transistors have been replaced by the 555 timer device. When a negative 0V pulse is applied to the trigger input, pin 2, of the monostable configured 555 timer oscillator, the internal comparator, comparator No1, detects this input and sets the state of the flip-flop, changing the output from a low state to a higher state. This action in turn turns OFF the discharge transistor connected to pin 7, thereby removing the short circuit across the external timing capacitor, C1. This action allows the timing capacitor to start to charge up through resistor R1 until the voltage across the capacitor reaches the threshold, pin 6, voltage of 2.3 VCC set up by the internal voltage divider network. At this point the comparator's output goes high and resets the flip-flop back to its original state, which in turn turns on the transistor and discharges the capacitor to ground through pin 7. This causes the output to change its state back to the original stable low value, awaiting another trigger pulse to start the timing process over again. Then, as before, the monostable multivibrator has only one stable state. The monostable 555 timer circuit triggers on a negative going pulse applied to pin 2, and this trigger pulse must be much shorter than the output pulse width, allowing time for the timing capacitor to charge and then discharge fully. Once triggered, the 555 monostable will remain in this high unstable output state until the time period set up by the R1x-C1 network has elapsed. The amount of time that the output voltage remains high, or at the logic level 1, is obtained by the time constant equation you see. A monostable 555 timer is required to produce a time delay within a circuit. If a 10 microfarad timing capacitor is used, calculate the value of the resistor required to produce a minimum output time delay of 500 milliseconds. If this time difference of 17 milliseconds, 500 to 517 milliseconds, is unacceptable, instead of one single timing resistor, two different value resistors could be connected together in series to adjust the pulse width to the exact desired value, or a different timing capacitor value chosen. We now know that the time delay or output pulse width of a monostable 555 timer is determined by the time constant of the connected RC network. If long time delays are required in the tens of seconds, it is not always advisable to use high-value timing capacitors, as they can be physically large, expensive, and have large value tolerances, E.G plus or minus 20%. One alternative solution is to use a small value timing capacitor and a much larger value resistor up to about 20 megaohms to produce the required time delay. Also, by using one smaller value timing capacitor and different resistor values connected to it through a multi-position rotary switch, we can produce a monostable 555 timer oscillator circuit that can produce different pulse widths at each switch rotation. We can manually calculate the values of R and C for the individual components required, as we did in the previous example. However, the choice of components needed to obtain the desired time delay requires us to calculate with either kiloohms, megaohms, microfarads, or picofarads, and it is very easy to end up with a time delay that is out by a factor of 10 or even 100. We can make our life a little easier by using a type of chart called a nomograph. Nomograph will help us to find the monostable multivibrator's expected frequency output for different combinations or values of both the R and C. So by selecting suitable values of C and R in the ranges of 0.001 microfarads to 100 microfarads and 1 kiloohms to 10 megaohms respectively, we can read the expected output frequency directly from the nomograph graph, thereby eliminating any error in the calculations. In practice, the value of the timing resistor for a monostable 555 timer should not be less than 1 kiloohms or greater than 20 megaohms. Bistable multivibrator with 555 timer. As well as the one-shot 555 monostable configuration previous, we can also produce a bistable, two stable states, device with the operation and output of the 555 bistable being similar to the transistorized one we looked at previously in the bistable multivibrators tutorial. The 555 bistable is one of the simplest circuits we can build using the 555 timer oscillator chip. This bistable configuration does not use any RC timing network to produce an output waveform, so no equations are required to calculate the time period of the circuit.
Bistable flip-flop circuit. The switching of the output waveform is achieved by controlling the trigger and reset inputs of the 555 timer, which are held high by the two pull-up resistors, R1 and R2. By taking the trigger input, pin 2, low, switch in set position, changes the output state into the high state, and by taking the reset input, pin 4, low, switch in reset position, changes the output into the low state. This 555 timer circuit will remain in either state indefinitely and is therefore bistable. Then the bistable 555 timer is stable in both states, high and low. The threshold input, pin 6, is connected to ground to ensure that it cannot reset the bistable circuit, as it would in a normal timing application. (555 timer output). In this part, we are going to check the keying and driving capabilities of the 555 timer, or, in fact, the dual 555 IC timer. The output, pin 3, of the standard 555 timer, or the 556 timer, has the ability to either sink or source a load current of up to a maximum of 200 mA, which is sufficient to directly drive output transducers such as relays, filament lamps, LED motors, or speakers, etc., with the aid of series resistors or diode protection. This ability of the 555 timer to both sink, absorb, and source supply current means that the output device can be connected between the output terminal of the 555 timer and the supply to sink the load current, or between the output terminal and ground to source the load current. Sinking and sourcing the 555 timer output. In this circuit, the LED is connected between the positive supply rail and the output pin 3. This means that the current will sink, absorb, or flow into the 555 timer output terminal, and the LED will be ON when the output is low. And this circuit shows that the LED is connected between the output pin 3 and ground 0V. This means that the current will source, supply, or flow out of the 555 timer's output terminal, and the LED will be ON when the output is high. The ability of the 555 timer to both sink and source its output load current means that both LEDs can be connected to the output terminal at the same time, but only one will be switched ON depending whether the output state is high or low. The two LEDs will be alternatively switched ON and OFF depending upon the output. Resistor R is used to limit the LED current to below 20 mA.
555 timer transistor driver. We said earlier that the maximum output current to either sink or source the load current via pin 3 is about 200 mA at the maximum supply voltage, and this value is more than enough to drive or switch other logic ICs, LEDs, or small lamps, etc. But what if we wanted to switch or control higher power devices such as motors, servo motors, relays, or loudspeakers? Then we would need to use a transistor to amplify the 555 timer's output in order to provide a sufficiently high enough power to drive the load. The transistor in the two examples previous can be replaced with a power MOSFET device, or Darlington transistor if the load current is high. When using an inductive load such as a motor, relay, or electromagnet, it is advisable to connect a freewheeling, or flywheel, diode directly across the load terminals to absorb any back-end voltages generated by the inductive device when it changes state. Thus far we have looked at using the 555 timer to generate monostable and bistable output pulses. In the next tutorial about waveform generation, we will look at connecting the 555 in an astable multivibrator configuration. When used in the astable mode, both the frequency and duty cycle of the output waveform can be accurately controlled to produce a very versatile waveform generator.